Find the reaction force, R, in newtons, required to hold the nozzle stationary. In this problem, water enters into a nozzle at point 1 and exits the nozzle at point 2, at a flow rate of 0.11 meters cubed per second. The absolute pressure and flow area at both ends are provided, as well as the mass and interior volume of the nozzle. The reaction force, R, can be computed as the root sum squared of the reaction forces in the x and y directions, Fx and Fy. We'll begin by solving for Fx. To do so, we'll set the sum of the forces in the x direction equal to 0, and then write out all the forces acting on the free body in the x direction. In this equation, Fx is the horizontal reaction force, which is what we're solving for. Variables F1h and F2h are the hydraulic forces exerted on the nozzle by the fluid entering at point 1 and exiting at point 2, respectively. And variables F1p and F2p represent the forces on the nozzle caused by the gauge pressure at ends 1 and 2. We'll begin by plugging in the variable theta, which accounts for the fact that the hydraulic and pressure forces at point 2 do not act entirely in the x direction. Next, we'll solve for the pressure forces, which equal the gauge pressure times the cross-sectional area. The gauge pressure equals the absolute pressure minus the atmospheric pressure. After plugging in the given absolute pressure values, as well as the atmospheric pressure, the gauge pressure computes to 98.7 kilopascals and 18.7 kilopascals at ends 1 and 2. After plugging in the area terms and converting kilopascals to newtons per meter squared, we find the pressure forces 1 and 2 equal 1,796 newtons for N1 and 151 newtons for N2. After substituting in these variables, we can revise our equation for the reaction force in the x direction as F1h minus 0.866 times F2h plus 1,665 newtons. Next, we'll solve for the hydraulic forces at ends 1 and 2, which equal rho v squared A, where rho represents the density of the fluid, v represents the velocity of the fluid, and A represents the flow area. From the problem statement, we already know the density and area. The velocity entering and exiting the nozzle equals the flow rate divided by the flow area. After plugging in the appropriate values, the velocities entering and exiting the nozzle equal 6.044 meters per second and 13.58 meters per second. Now we can compute the hydraulic forces at ends 1 and 2, which equal 664.2 newtons and 1,492 newtons, respectively. This makes the reaction force in the x direction equal to 1,037 newtons. Next, we'll solve for the reaction force in the vertical direction, Fy. If we set the sum of the vertical forces in the y direction equal to 0, then 0 equals minus Fy plus the vertical component of the hydraulic and pressure forces at N2 minus the weight of the water in the nozzle minus the weight of the nozzle itself. We'll isolate the reaction force in the y direction and plug in 30 degrees for theta. From earlier in the problem, we already solved the hydraulic force and pressure force at point 2. Therefore, all we have to solve for is the weight of the water and the weight of the nozzle. The weight of the water equals the density of the water rho, times the volume of the water, v, times the gravitational acceleration, g. From the problem statement, we know the density of water and the volume inside the nozzle. After plugging in 9.81 meters per second squared for the acceleration, the weight of water equals 58.8 newtons. Lastly, the weight of the nozzle equals the mass of the nozzle, m, times g, 9.81 meters per second squared. From the problem statement, the nozzle mass equals 10 kilograms, which makes the weight of the nozzle equal to 98.1 newtons. This makes the reaction force in the y direction equal to 665 newtons. If we plug in the reaction forces in the x and y directions, the total reaction force equals 1232 newtons. When reviewing the possible solutions, the answer is B.